and runs through a wiring grid that helps melt the ice. Now, over here you have your hot gas solenoid, which lets the hot gas come from the evaporator, from the condenser coil, and shoots it into the evaporator to warm up the evaporator quickly. Over here we have our water valve. So this didn't change, and this did not change, except for me adding the overload. But what we did change was we got rid of the ice thickness control, we got rid of the on and off switch, and we got rid of the bin thermostat, and we put this microprocessing board in. What does it do? Simple. This is what happens. You plug in your ice machine, it fills with water, the pump motor starts coming on, the condenser motor comes on, the compressor comes on. These three components are running. It starts to make ice. As it makes ice and the ice gets thick enough, the ice thickness thermistor senses the ice is thick enough. Well, the resistance changes to the specifications that are required to satisfy this board, and what it does is one or two of these relays will open up and shut off your pump motor and shut off your condenser motor. Meanwhile, your compressor keeps running. At the same time, it'll send power down here and power up your hot gas valve and power up your water valve. So now you're defrosting the ice off of the evaporator plate. You're filling with fresh water, getting fresh water back in there again. You've got your pump motor and condenser turned off. You got your compressor still running. You're going through your harvest, getting the ice off. When it's all off again, what happens then is this thermistor senses that it's warm enough. And when it senses it's warm enough, what does it do? It turns off the hot gas, it turns off the water valve, turns back on the pump motor, turns back on the condenser fan motor, and we go through the whole process again, making ice all over again. When the ice maker has filled the bin up, then the bin thermostat says, hey, I'm full of ice. I'm happy. What does it do? It changes resistance, feeds it to the computer board. The computer board recognizes that there's plenty of ice in the bin. What does it do? The computer board will turn off the power to the pump motor, the condenser motor, and the compressor. This whole section shuts down. Of course, there's no power coming into here because this is for defrost only, and that only occurs when this thermistor over here, which is your ice thickness thermistor, is satisfied. And that's how it works. It's that easy. It's really that easy. The board is in control of everything. The board is taking commands from the thermistors. They're telling it what the resistances are in different areas. It's picking up on what the resistances are by how the factory has it all set up to work. The microprocessor basically just carries out the commands that it's programmed to do by the resistances being changed through the thermistors. And that's as simple as it is. One of them turns it into a defrost mode, and the other one shuts it off. And here's your other on and off switch for your interface board. That's it. Now, this does not have a liquid crystal display. It's not programmable or anything like that. Basically, it's just an on and off switch. That's why I have one wire going to it. And your neutral, notice we have neutral. What's the neutral for? Power going into it. We got line 1 coming in. We got neutral. What's the neutral for? This board works on low voltage. So like we have a drop-down transformer over here to power up the heating grid so we can melt the ice when it falls off the evaporator plate. This neutral is supplying power to a step-down transformer on this board because this board has relays, and these relays usually work on low voltage. So what this neutral is doing is it's supplying the neutral in the line 1 coming over here, supplying the proper power to satisfy the primary winding on that step-down transformer so you can drop the voltage and operate all your electronic components, because CMOS chips don't operate on 120 volts AC. They work on low voltage, most of them work on DC voltage, so you must step it down and rectify it into a DC current. Okay? And that's it. That's the whole thing. If you want, you can study this one, go back and look at the other one. You can see the difference. Like I said, I left this the same, I left this the same. And you can see the difference on how electronics has played a role here. And it's doing the same job as the mechanical thermostats we're doing. And again, we added the overload. We can't forget our overloads on our compressors. They're there to protect them. Thank you so much, and I shall be back. Okay, what I put on the board here is a water-cooled system. It's a high-rise. It's an office building. You ever wonder how they cool large offices? 20-story buildings, 30-story buildings, 100-story buildings. There's different ways of cooling large buildings. This is just one example. When I get done showing you this example, rather than do a whole drawing on another example, I'm just going to explain it to you. Okay? What you have here is you have your office building. This building is approximately maybe about 6 or 7 stories high. What I put on the top here, this right here, is called a water tower. And water towers do not necessarily have to be on top of a building. They could be all the way over here somewhere. And all you have to do is run water to them. A lot of large schools do that. They'll put the water towers on the ground, and they'll run the water